All right, so we're going to start off from the very basics, just going back to the origin of chemistry. Does anybody know how chemistry originated historically? Why were people interested in chemistry?
Turning lead into gold.
Yeah, turning lead into gold. In fact, the first book that was released that really went into chemistry was this book right here. And if you look at it directly in the name, they talk about alchemy. So really, back in the Middle Ages, it was this hobby of primarily rich people trying to take non-precious elements like lead and convert them into precious metals like gold. Were people very successful at doing that? No. However, it kind of spun off into its own unique field. So let's really quickly describe the history of this. So it started out as alchemy, which is the study of how to make things into gold. And then that eventually evolved into chemistry. And we can actually see this in the terminology that's used. Both of these have that root chem in them, right? And then the founder of modern chemistry was Robert Boyle. He actually has some various laws named after him as well, like Boyle's law. And he essentially developed the field as we know it all the way back in 1661. And prior to this, people had a rough idea of what matter was made of, but they kind of had a loose understanding, not a fully accurate understanding. Really, when Robert Boyle put this book together, he said that matter must be made of atoms. And really, the whole idea behind an atom at that point in time was if you take a substance and you cut it, and then you cut it again, and then you cut it again, and then you cut it again, and further and further and further, you'll reach a point where you can no longer cut it and have the same substance, right? So he said that those smallest pieces must be made up of atoms or clusters of atoms. That are in motion. And it's kind of weird to think about it this way, right? So not only are atoms these super small particles, but they're vibrating and moving around a fair amount too. And so he was the first person to really start describing the molecular nature of atoms. The cool thing, like I was saying, is all of chemistry was essentially rooted in alchemy at first. However, today it's branched out into a variety of different fields. And that's one reason I love chemistry. Is chemistry can be related to all of these different subdisciplines. So it can be related to all sorts of healthcare fields, it can be related to plant life, it can be related to geology, to physics, to electronics manufacturing, to weather, to engineering, to ecology, to agriculture, to botany, to biology, you name it, it's related to it. One of my favorite quotes from my professor when I was an undergrad is biology is really chemistry, chemistry is really physics, and physics is really math. Really, when you look at science, it's this big continuum of ideas that are all linked together. So chemistry is interwoven into a lot of these other science fields. All right, how many of you took chemistry in high school? I'm just curious. So a handful of you? How many of you remember in high school or earlier talking about the scientific method? All right, that's good. So a few of you have heard of the scientific method, but I think it'd be good to review. The scientific method is at the root of all of these different fields, and it's a really important thing that scientists keep in mind anytime they're studying something. And the first thing that's always done in the scientific method is you just stop and you make an observation. All right, so for example, you might make an observation that a particular tree outside of your house is unusually tall. So you'd say, yeah, that's a pretty unique observation. Human beings are kind of designed by their very nature to see patterns in things. So when we see things that don't necessarily fit a pattern or things that are unique or unusual, we tend to make an observation. All right, after that, what we do is we tend to develop a question. So for example, if you see a tree outside your house that's unusually tall, you could have a question and you could make it as simple as, why is that tree so tall, right? And then after that, what do you think we are likely going to do? Anybody have an idea? Do we just stop there? What do you think?
To make a hypothesis?
Yeah, make a hypothesis. So that's a fancy word. So let's try to define what a hypothesis is. What does it mean when I say develop a hypothesis? What do you think? Yeah, make an educated guess about why something's the way it is. I think that's a really good answer. All right, so after that, what we need to do is we need to develop an experiment or a test, right? So we come up with some sort of testable prediction. Really, a hypothesis isn't a hypothesis if you can't test it, right? It needs to be testable in one way, shape, or form, because as scientists, we always like to test things. All right? Then after this, we want to gather data and test our prediction. All right, so that's a really important test. All right, so not only do we need to gather a lot of data, but we need to test it over and over and over and over again until we've got results that we are comfortable sharing with our peers, right? One of the worst things as a scientist is to not have enough data, make a false claim, and then be proven wrong, right? It's kind of like your friend rubbing something in your face. You don't want that to happen. So we go through and we test this over and over and over again. And then sometimes our data supports our prediction, we're able to make a claim, other times it doesn't. So what we need to do on occasion is we need to refine or alter our prediction. So it's okay to be wrong, but you most definitely don't want to go out and make a claim that's not supported by your data, right? At that point, what often happens is you go back and you make a new testable prediction. One of the hardest parts, in my opinion, of being a scientist is you get stuck in this self-feedback loop, kind of over here, where you're just going around in a loop over and over and over and over and over again, and oftentimes you're not even finding anything useful or anything interesting. You're just kind of stuck in this loop. But eventually, the hope is you will find something unique that is supported by your data, and you can go out and you can make some sort of claim based on the data that you've collected, right? At that point, what we do is we kind of get spit it out at this point, and we can develop a theory. What do you think a theory might be? Anybody have an idea? Yeah?
Your answer to why something is the way it is based on your data?
Absolutely. So it's kind of an explanation of why something is the way it is. You're basically explaining how something works or how you're proposing that it works. And really, a theory has to be supported based on your data. So the burden of proof is always on you, right? If you're going to say, the tree is tall because it got an abundance of sunlight and there's a fertilizer source nearby, you need to have data supporting that, right? So scientists have a lot of work ahead of them anytime they try to make a claim. So it is a fair amount of work. So let's go ahead and define some of these in a bit more detail, just so we have them in our notes. Oops. So the first thing I want to define, again, is hypothesis. And somebody had a really good definition of this. This was an educated, testable guess. And I'm going to put guess in quotes. A lot of people don't like the word guess in science. I'm okay with you using it, as long as it's based off of some sort of educated opinion. I think that's perfectly fine as a scientist about an observation. All right, and then at the very end, we said that we're going to develop a theory. And a theory is an explanation supported by data. And I'm really going to emphasize this explanation part. One thing that students often get confused with is the difference between something called a theory and something called a law. How many of you have taken like basic science where you covered laws? A few people? Yeah, so a law is a bit different. So laws commonly are used in classes like physics. A law is a summary of data. But it provides no explanation. So for example, if you think about Newton's laws, our classic example, he says that force is equal to mass times acceleration. Doesn't really explain how it works. He just says this is a math equation we can use to calculate force, right? So the trick I often use to remember the difference between a theory and a law is that a law is often accompanied by a mathematical formula. So anytime you're in physics or a class like that and they give you a math equation related to science, usually that's related to some sort of law that somebody's worked out. Does that make sense? It always bugs me too. Oftentimes you'll see on social media and things like that, people will say, well, that's just a theory. It's kind of like saying, well, that's just something you're supporting with evidence. That doesn't really refute what they're claiming, right? So theories are actually quite strong. That doesn't mean that they're weak. In fact, they're strong because they're supported by an abundance of evidence. Does that make sense? All right. The next part is a section I like to go over really quick called Critical Thinking in Science. And the textbook that you purchased has a really good discussion about this. And this is something I like talking about. How many of you have heard about like fake news in the media, right? So fake news is kind of creeping into science and people are getting really skeptical of scientists. I don't like that because science is all about not having a bias, approaching things with evidence, not having any sort of tilt or lean to it, right? And the system they use to describe how this works is called flares. And it's an acronym. The first one is F, and that's falsifiability. And basically what that means is that when you come up with your hypothesis, there needs to be some theoretical way for that hypothesis to be proven wrong, right? If all you're doing is proposing a hypothesis that can be proven right, that's really not a good hypothesis, right? So let's start out with that. So there must be a conceivable way to prove your claim false. That's a really important one. All right, the next one is L. That's for logic. And logic is exactly what it sounds like. We must use logical reasoning. It's a pretty important one. So we have to use basic common sense whenever we're doing science. We can't start going into the supernatural, for example. Next one is R. And that's reproducibility. And what that means is we must be able to replicate our data. This is actually a really, really big one in science right now. So I guess kind of getting on my little soapbox, oftentimes in order to work at a university, you have to publish a certain number of papers a year, right? So let's say I want to work at the University of Washington. They might tell me, in order to be an employee at this university, you have to publish 4 papers a year in high-end journals, and we're going to be really critical about what journals those are in, right? So this creates a lot of pressure for scientists to constantly push out papers. However, sometimes they get a little bit sloppy. The one field that's kind of been picked on recently is psychology. There's been a lot of psychology papers where people go back, look at those papers, try to reproduce the results, and they can't. So there's a lot of concern that maybe as scientists we need to slow down, we need to double check our data, we need to have independent third parties double check our data and make sure that all of the data we collect is reproducible. All right, and then the last one is sufficiency. And this kind of gets broken down into a few different areas. The first is that the burden of proof always lies on you, right? So you have the burden of proof. You can't just go around making claims that aren't backed up by data, right? So you can't just go around the streets of Tacoma saying, I saw Sasquatch, without having some sort of photo to back you up, right? Otherwise, people think you're a little crazy. All right? Along with that is that extraordinary claims require extraordinary evidence. So again, going back to my Sasquatch example, let's say you did see Sasquatch, and you're going around the streets of Tacoma with a grainy photo. Is that going to be very convincing for people? No, probably a photo, even a good photo wouldn't be good evidence. You would need a lot of data to claim that you saw Sasquatch and that it actually was Sasquatch and not a man in a gorilla suit. All right, the next one is one of my favorites. There's correlation. Does not equal causation. And we've seen a lot of this lately in the news, especially with vaccines and things like that. So for example, the big thing that was in the news was about vaccine and autism, right? A lot of people are talking about the anti-vaccination movement and the measles outbreak in southern Washington. And a lot of that was due to a scientist back in the 1990s that was kind of looking at this, and he did some kind of bad things when he was publishing his data and was cherry picking results. But a lot of people looked at this and they said, we're giving children a lot more vaccinations and the rate of autism is going up. Maybe the two are linked. No, we've done a lot of studies basically saying those two areas are not linked in any way, shape, or form. And one of my other examples I like to use to kind of show this is maybe we could claim that autism is due to the increase in organic food sales. If you actually chart this together, the best fit line is 0.9971. That's a really good correlation, right? Is that causation? No. So again, that kind of goes back to the burden of proof, that if you do want to link two things together, you have to have a control group, and you have to have a testable group, and you have to have really, really, really solid evidence if you're going to make an extraordinary claim like that. All right, and then the last one is also important. And this is authority is not evidence. One of my favorite examples of this has to do with the discovery of DNA. Does anybody know the shape of DNA? It's kind of a spiral, right? It's called a double helix. Prior to the discovery of that structure, there was a chemist, And that chemist actually had 2 Nobel Prizes. He had one in chemistry, and then he had a Nobel Peace Prize. He was arguably the most famous living scientist at the time, and he came out with a paper at the time saying, you know what, I think it's a triple helix. Basically, everyone was like, oh yeah, he's smart, I trust him. Really what they found out was he was completely wrong. All of his assumptions were based off of just his own claims and not really supported by evidence, and it was kind of a big embarrassment for the field that they just went along with this guy because he was famous. So we always have to go back to the sufficiency thing, right? You have to have a ton of proof. Anytime you're making an extraordinary claim, you have to have an abundance of evidence to back it up. Correlation is not causation, and authority is not the same thing as evidence. So even though you're famous or people respect you, we shouldn't trust you based on your name alone, right? You always have to back it up with a lot of data. Make sense? All right. So that's kind of our brief intro into science. I am a big believer in following all of these rules, mainly because as a scientist, we want to kind of stay out of that area where it's opinionated and political and biased and things like that. We always want to back things up with an abundance of evidence. All right, so what we're going to do next is we're going to jump into physical properties. And this is actually linked into what we're going to cover tomorrow in lab 2. Yep.
In Ferris, the E, you capitalize E, was there no E?
Yeah, that's a good question. This textbook, I don't know why they came up with this acronym, but I think they got the E from the RE in reproducibility. It's not the greatest acronym in my opinion, but it kind of gets the point across. Good point. All right. So physical properties. Does anybody know what a physical property is and how we could define it?
The state of changing matter.
Close. So that's more related to a chemical property. So if we're changing matter into a new type of matter, that would be a chemical change. We can have physical change, though. What would a physical change be? Yeah, so maybe boiling water, right? It's still water when it becomes steam. So in that way, you're entirely right. So it depends kind of how we're describing the change, right? Are we changing something into a new substance or a new state? So let's describe this in a bit more detail. Physical properties are hugely important in science. They are things that can be measured or observed without change. Without changing matter into a new type of matter. We'll talk about this in more detail. We can undergo phase changes. However, we're talking about making measurements without changing stuff really at all. Yep.
Isn't there 4 states of matter? There's solid, liquid, gas, and plasma?
Yeah, exactly. We'll talk more about that too. So there's 3 main states of matter. There's solid, liquid, and gas, which is what most of us learned in elementary school. But you also brought up another one, right?
Yeah.
That was plasma. Does anybody know a good example of plasma? Lightning?
Oh.
Fire? So those are still states of matter. They're just kind of unusual states. So this textbook tends to stick with solid, liquid, gas. Plasma is unique and interesting though. All right, so let's think about physical properties. What are things that we can measure without changing a substance? So think about things you might measure in your house. What do you think? So we could measure water. How do you normally measure water? So if you say, I want water, how does the person you're asking know that you want a cup versus a swimming pool size amount of water? Yeah, and we can measure that with something called volume. So volume tells you basically how much of a liquid you're asking for. So for example, if you look at a Coke can, that might say 355 milliliters, something like that. Or if you go down to the vending machine, it might say 20 ounces. Both of those are volumes telling you how much of a liquid. So we can measure that without changing Coke from Coke to something new. What else can we measure? What do you think?
Maybe like the weight of the color.
Yeah, so weight. I'm going to change that a little bit, and we're going to call this mass, but we'll come back to this because there's a fine distinction between weight and mass that we'll get back to. All right, anything else? You said color. So we can actually measure the color of a substance without changing it? Yep.
The density fall under mass?
Yeah, so density. In fact, we'll come back and talk about density here in a minute, but density is correlated to mass and it's correlated to volume. So we'll kind of go back and cover all three of these again. Anything else? Yep. The shape? Kind of. So shape can be a little bit tricky. Let's say you go to the doctor's office. Oftentimes what they're doing is they're measuring your mass, right? So you get on a scale. What else? Height or length, right? So you can measure shape in that regard, right? So height, length, width, things like that we can measure using a tape measure. What else do we often measure in our home? Think about on a really cold day, what might be a concern? Temperature. So your house could be hot, it could be cold. What else could we measure potentially? Humidity, we can measure humidity. There's a few other ones that are really important for chemists as well. I'll kind of get us along here. We've got boiling point and freezing point. And chemists really like talking about these because it varies depending on the substance you're talking about. So for example, water has a boiling point of 100 degrees Celsius and a freezing point of 0 degrees Celsius. However, methane, meaning the main component in natural gas, might have a very different boiling point and melting point. So oftentimes we can investigate a type of matter by looking at its freezing point or its boiling point. Another one that's pretty interesting is hardness. This is important in geology. Does anybody know what the hardest substance is that we know of? Diamond. Does anybody know how we cut diamonds? With other diamonds, right? It's the only way we can cut diamonds. So diamonds are pretty unique in that way. Everything else is measured based on how hard it is relative to a diamond. So if you go into the jewelry business or geology, you might talk about that. The other one that's a bit more abstract is we can actually measure odor. So, did I spell that right? Is it? Okay. Like looking at it, I'm like, ah. All right. So odor we can measure. If you live down close to downtown, you might have picked up a unique odor. You can actually go through and sample the gas in that area and pick up the amount of a given compound in the air and measure odor that way. It's pretty unique. I heard the refining plant had a busted pipe, and that's why downtown smells like rotting animals right now. There's a few other ones we can measure, but this is a pretty good list. The big takeaway from this is we're measuring things without really changing the substance in and of itself, right? So now what I want to do is go back to those starred ones, so volume, mass, and density, and talk about those in a bit more detail. So the first one we'll go over is mass. So we said that we're going to use the term mass preferentially over weight. Does anybody know why? What do you think?
Your mass stays the same, but your weight can change.
Yeah, so your mass can stay the same, but your weight might vary. Why might your weight vary? What do you think?
With gravity, so when astronauts go to space, they weigh their mass is still the same.
Exactly. So the example you had was when an astronaut goes into space, his or her mass doesn't change, right? But they're weightless. So weight does depend on gravity, where mass doesn't. Yep.
Because isn't it kind of like mass is like I guess kind of the amount of space you take up and just
Close. So you're talking about the amount of space you take up. That's a bit different. That gets more into volume, but what we'll do is we'll link those together with density. That's a great point. So mass is an intrinsic property. Weight, on the other hand, depends on gravity. All right, so let's talk about how mass is measured. So in the United States, how do we normally measure our mass? So if you step on a scale at home, what is it in? Pounds, exactly. And the abbreviation for pounds, most of you are probably familiar with, that's the LBS symbol. All right, Americans are notoriously stubborn though, right? How does everybody else measure mass? Kilograms. They usually will measure it in grams or in kilograms. And the symbol for grams is just lowercase g, where for kilograms it's kg. What we'll do later is we'll talk more about what this prefix means. That kilo that goes in front of grams means 1,000 grams. So we'll talk more about all of the different prefixes we can use to indicate the magnitude of something. Yep.
Is it only the UK that uses stone?
So the United Kingdom uses some other imperial units like stone. Yeah, if we ever work with that, we'll give you some conversion factors so we know how to flip-flop from one to the other. There's a lot of weird weight measurements that were developed in the Middle Ages that people kind of hung on to for a while. Really today, scientists decided as a community, let's try to stick to the standard one. So most scientists will measure things in grams and kilograms. So usually when you go to the doctor now, I've noticed, when they tell you your weight, they normally tell you it in kilograms because the medical community is trying to get on board with this as well. Does that make sense? All right. Next one we're going to talk about is closely related, and that's volume. So volume is different than mass. Mass is just basically how much you weigh on Earth, right? So it's completely the same on Earth. We know it changes, though, if you change gravity. What about volume? What does volume tell you about? Does anybody have an idea? The amount of area you take up, right? So volume is basically the amount of area you take up. And it's a pretty easy thing to measure. What people often do is they'll get some sort of container. This is called a graduated cylinder, at least my artistic representation of one. It's commonly used in a lab, and on the side what you'll see are these little numbers. Whoops, maybe it'll be 10, 20, 30, whoa, I can't write today. 40 and 50. And what we'll do is we'll fill this up with some water like that. And then what you could do is you could take an object, maybe it's this red circle, and you can toss it in here, right? So throw it in this container full of water. What do you think will happen to that level of water? Will it go up or down? It'll have to go up, right? Because that red ball has to take up some area. All right? So we'll do the best with my drawings here. So maybe at this point it goes up like this, and our red ball is now in the bottom. All right, let's assume that this is being measured in milliliters, right? So all of these are milliliter units. That's a unit for volume. What does that tell you about the volume of the red circle? Yeah, it's got to be 10 milliliters, right? Because we went up 10 milliliters. So it's the amount of area that you displace. So that's a really easy tool we can have to determine volume, especially for objects that have irregular shapes. If it's a true sphere, we can also do that using mathematical equations. However, we know in reality, it's a lot harder to do if you have an irregular shape like a human being. If you want to find the volume that you displace, you're not going to be able to do that using a mathematical formula. But what you could do is jump into a giant graduated cylinder and see how much the water goes up. So you could do it that way. All right. Like I said, chemists like to measure things in milliliters, which has the prefix ml. Usually it's a uppercase L, however, occasionally you might see lowercase l's. And this is what chemists usually use to measure the volumes for liquids. So like I said earlier, if you pick up a Coke can, on the outside bottom, you'll probably see I think it's 355 or 353 milliliters. That tells you the volume of Coke on the inside of that can. For solids, we use something a little bit different. We typically use something called centimeters cubed. And the symbol for that is cm to the third power. And that's normally used for solids. And I'll kind of show you what that means. So let's say, we've got a cube over here. A centimeter cubed means that it's something that is 1 centimeter tall. It has a width of 1 centimeter. And it's got a depth of 1 centimeter. This is equal to 1 centimeter cubed because it's 1 centimeter multiplied by itself 3 times. And if you work in the medical field, you might even see this written as 1 cc. That's kind of shorthand for centimeter cubed. So oftentimes, if you get an IV, they might refer to a cc of something being added to that IV. That's a centimeter cubed. It's a volume measurement. It gets kind of confusing because all of these can be used interchangeably. So what I mean by this is 1 centimeter cubed is equal to 1 milliliter is equal to 1 cc. However, chemists as a community tend to prefer the unit of milliliters over cc or centimeters cubed. And that's typically because we're dealing with liquids that are most easily measured using something like a graduated cylinder. Does that make sense? All right, and then last but not least, we're going to tie these two together through something called density. And the best way of describing density is, let's say you have a softball, right? So most of you have probably felt a softball. You can imagine that weight in your hand or what it feels like. And then imagine the same size sphere that's made of lead. Those could have the exact same volume, but would have very different properties, right? So if you've ever done track and field and tried to pick up a shot put, they're really heavy. They're not at all the same mass as a softball. So we have to come up with a term to talk about the difference between them. And that term is density. So density can be measured as the mass of an object divided by the volume of an object. And if we want, we can kind of turn this into math terms, right? So D can be abbreviated for density. Mass we turn into M, volume V. So we can turn this into a little math equation, right? And then we've also got to consider the units. So the units that most chemists use for mass are grams. Or we often use grams over centimeters cubed if we're dealing with a solid. So this is normally how chemists will measure it. I will make a note that this is preferred by chemists, but physicists might use something else. So it really does depend on your subfield. I've seen physicists where they use kilograms over liters. Really, they're similar units, but chemists, for the most part, tend to use grams over milliliter. All right, the neat thing with this, though, is if we think about it, all it really is a math equation. So let's do some games with this math equation. We said that density is equal to mass over volume. All right, how can we calculate mass using that equation? Just using basic math.
The density multiplied by volume?
Yeah, the density multiplied by the volume. So if we're given the density and volume of an object, we can find its mass. And then same thing with volume. How can we figure out the volume if we know the density and the mass? Close. It'd be mass divided by density. So we do have to make sure that we set things up so that they're in the appropriate orientation. So the correct number on top and the correct number on bottom. So we can actually use this to solve a variety of problems. All right, so let's take a look at some examples. Let's think about the density of water. And I'm going to be specific here. I'm going to say at room temp. Does anybody know what the density of water is at room temperature? It's a nice number. It's not a hard number to remember. One, exactly. So it's usually about 1.00 grams per milliliter. And like I said, we have to have those units in there. And the units, like we said, are going to be the mass units, which are grams, divided by the volume units, which are milliliters. You could, if you want, write this as 1.00 grams over milliliters, or you could even write this as 1.00 grams over milliliters. It kind of doesn't matter. All of these are the same way of writing that answer, right? Why do you think I included the at room temperature part? Yeah, temperature is an external variable. Do you think the density of water might change if we cool it down? Yeah, absolutely. If you have an ice cube, is it going to be more dense or less dense than liquid water? Less dense. It's going to want to float and rise to the top, right? So then we can think about it that way. So the density of ice kind of depends on the source, but it's going to be 0.915 grams per milliliter, at least using the source that I was looking at. So because it has a lower density, it tends to float, right? So things that are less dense will float, things that are more dense will sink. All right, my other favorite example is Mercury. And I don't mean the planet, I mean the element. So if you look at the periodic table, at number 80 over there, it's kind of the green symbol, Hg. That's Mercury. If you notice, it's close to the bottom of the periodic table. That means it's very, very, very dense. Typically, things get more dense the closer to the bottom of the table you get. So Mercury is a pretty unusual element. It is a liquid, but it's also a metal. How many of you have seen Terminator 2? So Terminator 2, you remember they kill that Terminator, or they don't even kill it, they freeze it with nitrogen and then shatter it, and then it turns into a liquid. It kind of looks like that. It's a crazy metal. The weird thing with Mercury, though, is its density. The density of Mercury is 13.53 grams per milliliter. If you get a cup of mercury, you can take pennies or quarters or anything like that, and you can actually put them in that cup, and the penny will actually float on top of the liquid. because even as a solid, it's less dense than this super dense liquid. So mercury is an incredibly strange element for that reason. One reason I'm not allowed to use this in class, though, has to do with the nature of mercury. What's wrong with it?
Poison.
It's poisonous. So how many of you have heard of Mad Hatter's disease? So Mad Hatter's disease was due to these guys that used to make hats in the late 1800s, early 1900s that worked with mercury. And then after a while, they went crazy. So if you've read Alice in Wonderland, they talk about the Mad Hatter. That's due to the neurological disease that those people got. So mercury is really bad for your neurological system. Other than that, I think we're going to stop there. Again, I wanted to reiterate that tomorrow we're going to meet across the hall in the chemistry lab. Please read through the Penny's Lab handout, prepare your lab notebook, and then watch that pre-lab video as well. It should be a pretty short lab, just an intro into safety procedures and lab equipment.
Are we turning in the